In this scenario, we're going to be creating an adaptable parametric panel using CATIA generative shape design, in which we'll be using wireframe, surface, and volumetric features to create an adaptable model. So we start off by creating a container for our features, our parametric features, and we're going to specify an input for this adaptable model. Now to start off, our input might just be a simple flat surface, which we would specify in a sketch and create a fill surface from that sketch. But that's really not going to give us exactly what we need. We're going to be looking for something a little more curvilinear and a scenario that is more challenging for this particular panel. So we're going to create a set of sketches on planes that, and then a sweep, which will create for us a doubly curved surface. And in addition to this doubly curved surface, we want to make sure that the orientation of that surface is in the right direction. So we're going to be facing it up in this case. And we want to extract the boundary of the surface. And we want to break that boundary down into its discrete edges. The edges, it's important, all go in a particular direction because as we build up our features, our model features, those will depend upon the directions of the curves and the surfaces that we start from. So we need to be very specific about how we set that up initially. Now we're just going to organize our features, and I like to kind of collect them together into a construction geometry set. So for short, ConGeo, but that's just to collect all of the features which together make up the steps for creating that piece of the model. And I'm just going to clean things up a little bit and rename them so that I have my input surface specified and all of my input curves. Curve 1, curve 2, curve 3, curve 4. This being a four-sided panel surface. So now that we have our inputs set up, I'm going to start to model this adaptable panel. And to start off, I want to select the edges and start with the first edge. I'm going to create a point, and I'm going to make that point at the end of the curve. So it's going to have a ratio of 1, 0 being the beginning, 1 being the end. And the same goes for the upper curve. I'm going to do the same thing. And then I'm going to create a line that is a point-to-point line between those 2 points. And then add a midpoint to that line. So now I've got a midpoint, and I want to now take that point and project it to the surface. So I now have a point sitting on the surface, and it's going to be a starting point for the additional lines I'm going to add. So now I want to add a line that's normal to that surface from that point. And you can see now that that's sticking up 100 millimeters from the surface. I'm going to add another endpoint, again, ratio of 1. And I'm going to add a perpendicular line that will be the middle of this cloverleaf shaped panel that we're going to model. I need to specify a plane direction. That's important. And then I'm going to use that plane as the direction for this perpendicular line that's coming from the vertical line on the surface of the input surface. So now I've got the middle portion, and I'm just going to add one more plane, which we'll see in a little bit why I'm adding this plane for the final curves I'm going to draw. Now I'm going to set up the edge condition also. I'm going to add another point that's a midpoint on that edge. And I'm going to create an intersection. Oh, first I'm going to create a plane that is on that line, and then I'm going to create an intersection. And that intersection is going to be between the plane and the surface. I'm going to create a line that's tangent to that curve, so that I have now a line which sits tangent starting from that midpoint along that intersection curve. I'm going to take those set of features. So I've created those 4 features in the model. I'm going to collect them together in a geometrical set, turn off a couple of them so that I just see the plane and the line. And now I'm going to look at the inputs. So now I've collected those set of features. I can see that there's a surface and a curve that are the inputs. So now I'm going to copy those collection of features, and I'm going to re-specify their inputs. So I can take any features I've created, copy paste them, and repurpose them very quickly. I don't have to create additional ones. I can just copy paste and alter the inputs, and I have brand new set of features. I'm going to do the same thing for the other edges. And once I'm done there specifying the different edges, I'll do an update to the model, and I've got the starting point for this parametric rigging. Now this final step before I create the surface is to create a spline between these edges. And in addition to the endpoints, I'm going to specify the tangent direction. So that's where I need the planes. That's where the planes come in. I'm going to tweak the directions of those planes. And the curve looks good, but I just want to tweak the tension a little bit. So it's a little too sharp. I'm going to look at the middle one there, I think, and add a little more and then soften that curve. So now I've got a nice smooth transition. I'm going to do the same thing on the other side. I'm going to select those endpoints, specify their tangent directions, and tweak those tension numbers so that I have a nice smooth curve. And now I have all the curves that I need to create this cloverleaf shaped surface. So now I pick the fill feature, and I'm gonna pick each of the edges in order, and I want to make sure that I've picked the final one. And now it says I have a closed contour, perfect, and I can preview it. Looks great. The only thing I want to do is make sure that the next panels over are continuous with this panel. So I'm going to pick the input surface as a support. And what that's going to do is it's going to create a tangency with this fill surface and the input surface. So when I do update, you can see it lies a little flatter now, so that for any surfaces next to it, there'll be tangency continuity between them. So now I have the surface. I want to create a thick surface from that, create a volume. I'm going to add a thickness of 10 millimeters. And because the surface has such a clean geometry, it easily thickens. You can see it's got a nice clean edges to it, and it transitions nicely. So now that I've got all these features I've created and all this history to the model, I'm going to collect it together and just kind of like I did before and collect it into a construction geometry set so I can turn things off if I need to. But I still have all that rigging, all that line work to reuse whenever I want. I'm just gonna now specify the names of all of these. So this is going to be half the panel, the surface, and the volume. And now I want to look at the parametric inputs for this panel a little bit. Now I'm going to switch to the engineering rules capture app in order to create containers for the parameters and formulas which drive this parametric template. If you only have the building designer role and do not have the engineering rules capture app, you can create these on the fly from the Tools tab and then copy paste them into your geometrical set. I'm going to create a panel width parameter, a panel depth, so that'll be for the distance from the input surface, the amount that it'll lift off the input surface, and the thickness of the volume, the thick surface volume. Now I'm going to go through here and find the features that have those parametric inputs. I'm going to connect them to the parameters that I've created. So I'm going to look at the edge lines that I set up, and then those are 50 millimeters. So I'm going to connect that to the panel width. And same goes for all of these. A quick shortcut is I can add an equal sign and automatically connect those parameters to the inputs of the features. And then I'm going to also look at the volume thick surface and connect that to the panel thickness. So now I'm going to just test it out a little bit. Let's see what I get if I bump that up to 150. Okay, I see the middle there hasn't updated. So I'm going to just go in there and add that parameter input too. So now I have all the edges updating based on that parameter input. And looks like the panel depth is working fine. And the panel thickness. So now that I've tested that, I'm just going to move those formulas into the relations container that I've created there. So now everything is together inside this panel geometrical set, this container. And I want to make sure to do that before I create my parametric template. So the thing I'm going to do now is take those set of features and copy paste them into the panel geometrical set that we created and start to specify alternative inputs. And once I've done that, you can see that I've taken all those features I created before and I've repurposed them for the other portion of this panel. Now all I need to do is update the direction so that this other portion of the panel now will go in the opposite direction from the input surface. I didn't have to recreate those features. I just had to repurpose them. So it makes it very simple and quick to model. And I'm just going to hide the construction geometry. Make sure I rename things properly so it's easier to find later. And there we go. Now I've been able to go from a brand new part file straight to these parametric adaptable model portions. And I'm going to take a look, see what that looks like in the Building and Civil Assemblies app. So looks right, looks continuous. The two panels fit together nicely. And they show a nice continuity. Now I'm going to take this parametric adaptable panel I've modeled, and I'm going to test to make sure the parameters are working as I expected and everything is hooked up correctly in preparation to make a template from it. So I'm going to tweak all those numbers and see that it's updating as I would expect, and yeah, looks good. So now I'm going to turn them back, the parameters back to the original values, and I'm going to start to set up a user-defined feature, or UDF, which is a type of template in CATIA. So I'm building engineering and 3D design. Under tools, I'm going to go to user feature. And I'm going to select that panel geometrical set, which contains all the features, parameters, and formulas that we've created. I'm going to make sure all the inputs are there. They're automatically determined in CATIA. And I'm going to expose the parameters so that when I instantiate the user-defined feature, they'll be there. I'm going to switch it from black box to white box so that I can see the features when I instantiate them contained just for any testing. And now the outputs will be the two volumes of the two different portions of the panel. So now that we've created that UDF, that user-defined feature, we're going to test it out a little bit to make sure it's working as we expect. So we're going to create a panel instantiation test, just a temporary geometrical set. And we're going to try out testing this. So it gives us a little preview of the original template, what it looked like with the panel and the input curves. And we can see we want to pay close attention to the direction when we're instantiating a template, we want to make sure that we're picking the right elements and the elements are going in the right direction from the original model. And once we've done that, you can see, all right, we now have this user-defined feature with the panel, the parametric inputs exposed, and we can update it just as we'd hoped and expected. Now that's pretty straightforward because we just used the input that we set up from before. So the real challenge is if we were to test this on a different context. So here we are at a set of surfaces, input surfaces and input curves that are very different from the original context we created. We're going to instantiate this user-defined feature, and we're going to select the input curves in order, and make sure to repeat so that we can do it multiple times. And we're just going to go through this a few more times. I'm going to speed this up a little bit so that we have a few panels instantiated. And that is going to give us an idea of what it would look like if we instantiated these UDFs across an entire test surface. So it's looking pretty good, pretty clean. It's no errors. We have been able to get something that adapts pretty nicely to a different context. The next step will be to actually look at the skeleton that we've created and start to set that up with the template. Now we're going to look at the skeleton surface that we're going to use to instantiate the template. So we have a surface that was modeled originally in X shape, a subdivisional surface, and we've applied a dividing workflow in Generative design. So we take the input surface and we divide it up. We have a divide node here that divides into discrete input surfaces. And we want to specify the center of that surface and add an axis system. And then take the edges of those surfaces and make sure that they're in the correct order. So originally, they're not in the order that we need them in. So if we add a polar sort to this, we can get them going in the correct direction, starting from the bottom clockwise. And so we have a set of curves going in the right direction and the right orientation too. And that's all very important. So once we've broken it up into these buckets of these inputs, we've got our bottom curve, side curve, top curve, and so on. We're going to, this is all connected so that if we wanted to, we could go back to the original form that we created in X shape, the subdivisional surface, and we could start to push and pull this surface, and everything we've laid on top of it will automatically follow. So if we go in here and edit the subdivisional surface, and we select a point that we want to push and pull, just like digital clay, we're going to, we can we can specify how far we want to drag that. We can be pretty specific about the distance. And so I'm going to pull that out just about a meter. And you can see it's bulging. The surface is kind of pushing in. And once I complete that, all the other elements I laid on top of it in Generative design will follow. All of the axis systems and edge curves that we need as input when we instantiate the template. Now, if we go back into the template itself, we need to set up a type. So in this case, we're going to say it's a plate and create a plate type. And make sure to set it to adaptable because we want this to be an adaptable panel. And now we're going to specify the user-defined feature, the UDF, that we created originally, the panel UDF. We're going to make sure that that's part of the panel type. Once we've done that, we can go into the context that we've set up, the parametric skeleton, and start to specify how we place these panels. So you can see all of the inputs are broken out in multiple sets. And since we just created that new panel type, we're going to choose it and select the axis systems that we set up in our Generative design workflow, and all of the input curves and input surfaces, the bottom, left, top, right surfaces, curves, edge curves. So once we've done that, we'll have a specification, these specification objects, which will allow us to automatically apply the template to the skeleton. And we can also update the parameters. So when it instantiates, we can specify the parameters that are set. So if we go up a level and specify the level of detail, level of development, I should say, we can expose those features, those user-defined features. And this will automatically now apply those user-defined features we created to this skeleton context. Now that it's done, we can take a look and we can turn off hide the skeleton and take a look at the results. It looks like we've done a fine job of getting these panels to follow this changing surface. From this single adaptable model, we've created a number of design variations. And we're now going to look at them on the web. So in a web browser, in the 3D experience, we can view the models and see their full complexity on the web. Now this first option is a very simple one, just a flat surface with all of the units instantiated. But we can see that we've also created a revision to that. So we have a revision to that original option, which takes the spacing and adjusts it a little bit, makes it a little narrower at the edges, a little broader in the middle as a different option. But in addition to that, we've also created some branches from the original design. And those branches show a design that's more curvilinear, where the center starts to push in. And even further than that. So we see the option with it pushed in, and we also can see one where the form is even a little more sculptural, coming down on one side and wrapping around. All of this being done in a web browser. In addition, we can also see it in the thick client in CATIA and view them together in this way too, and examine the different options that we've created, the revisions and the branches. We can also work at different scales, like at the scale of a building. So here we have an input surface at a building scale that was originally modeled as a subdivisional surface. And we've divided it up using Generative design into individual panels and their edges, their respective edges, just like we did before. And we can apply that panel at the building scale. We can see the variation and how it would work at that scale, viewed from inside and outside. We've also added the ability to unfold this surface and look at how the difference in the way that the surface stretches when it's formed from a flat sheet. So here we have a heat map view of this flattened surface, and we can see how much it's changed. So like this panel has changed less than 1% in terms of its deformation. And we can see that it's deforming where it's about 1 or 2% deformation in different areas. So we have very specific design for manufacturing assembly information coming out of the model, even early in design. So in review, we started modeling a panel template by aggregating a series of basic 3D geometrical elements, planes, points, lines, and curves, to form an adaptable wireframe. We were able to reuse the model features a smart way, create a complex surface, give it a thickness, all while ensuring that it could be used in various contexts. We were able to quickly apply this template to a variety of iterations and scales, from architectural feature wall to a building facade. We achieved design complexity quickly, from simple beginnings using CATIA generative shape design in the cloud.